Concurrency in Go is awesome. Listen, I like Go, you like Go, we all like Go. Concurrency in Go is exceptional due to how easy and lightweight Go routines are and the communication mechanism called channels. These two tools allow for efficient execution of tasks, API calls, aggregating data, whatever you want. You can do it so easy with our built-in tools from Go. And if you don't know what concurrency is, don't worry. Concurrency is the concept of executing multiple tasks at the same time. This improves your program efficiency by utilizing all the available resources on your computer and not just one per the execution. A good example of this is, let's say you have to read a CSV file that has millions of rows. You can read each row one by one by one by one by one, or you can write a Go routine that can read a bunch of rows at once and then move on to the next uncompleted unread row, which is so much faster. It's going to save you time. So in this video, I'm going to show you with an actual example that calls a real API, even though it's free, and pulls data from it. All right, so you can see here, I have a very simple main.go file with just one function called fetch weather. And all fetch weather is doing is it's calling the openweathermap.org API by passing in a city, which is a string, and an API key, which I have, oh no, leaked here. Now, again, openweathermap returns the temperature for the city that you pass in. So it doesn't do anything fancy. So let's first declare our list of cities. So let's make this an array, string, and then pass in Toronto. Let's go with London. Let's go Paris, and let's go finish it off with Tokyo. And let's iterate through our cities and pass each city into our fetch weather function. So we can ignore the index city, in range cities, data is fetch weather city, and let's just write for fmt.print line, this is the data, and pass in data like so. And this is all we're going to do. However, like I said, I'm interested in the benchmark. How fast or how slow will these two methods compare? Awesome. So without further ado, let's go ahead and run this. So go run main.go. And you can see there, we're getting the temperatures for our four cities. For Toronto, London, Paris, and Tokyo, we get our temperatures, and the total time this operation took is 384 milliseconds. And we can run it again just to be sure. This one took 406 milliseconds, and one last time it took a full second there. I think that may have been just something to do with the network, or I'm getting stopped, but you can see that it's taking roughly between 300 and 400 milliseconds on each request. But can we go faster? Can we do this better? So the first thing we're going to do is modify our fetch weather function. And the first thing I want to do is pass it in a new argument, a channel argument. It's going to be a string. And we're also going to give it a wait group, which is going to be a pointer reference to sync.wait group. And the first thing I always like to do when I know functions will be called in Go routines is put my defer wait group done call here, and this assures us that we'll close and send the signal to our primitive, which is our wait group, to finish off, and that this Go routine has completed. And here, right above return data, we can do instead use our channels, and we can do fmt.sPrint format, and we can put this is the, and then here put city. Now with those arguments out of the way, let's actually declare them. So channel is going to be make.
So, if you ever wanted to 10x the speed of your app, well, this probably won't do that, but it will probably increase the speed of your app, probably. Disclaimer, you know, you have a certain use case, it might not do it, blah, 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 blah. You get the picture. But today we're We're going to be talking about concurrency, parallelism, and Go routines. One of my favorite features of the Go language and something that I think not nearly enough people understand and utilize. So today I want to break down in simple terms how all of this works, how to use it, how to implement it, give you some examples, get you on the right path, and yeah. Before we get into that real quick, make sure you guys are subscribed. I'm gonna have new stuff for Golang coming out every single day for the next, I think it's like 40 something days, all the way through February 28th. Make sure you're subscribed. Make sure if you like the video, you do so. And yeah, with that said, let's start breaking down concurrency, parallelism, and Go routines. So I think the best place to start with all of this is with a very visual example. So first and foremost, what does a Go routine do? A Go routine is going to spin out a separate process from your original one. So if we imagine we have right here, we have our main process running here. So when we start up, we execute func main. This var wg is going to happen right up here, and then we're going to add on one. So we're all just executing down the line of our program. But then when we hit this Go routine right here, we're going to spin off another arrow that's going to be running over here. So we're going to spin up for this go func right here. We're going to spin up another thing running right here. And then when we go back down here, this will be executing at the same time as the rest of this. So these two start running in parallel or concurrently. We'll talk about the difference in a moment here. So we spin off another instance, which is going to be running here. And then once we go down here, this wg.add1 is going to be happening on this original thread. Then when we hit this go func again, we're going to spin off another one, and we're going to be running it here. So these are going to be running, but the main program is going to be on this one. So then when this one terminates, the whole thing is going to terminate. These are just going to be left dangling, and they're just going to disappear into the void. So we need to make sure that we have a blocker here. So this wg.wait is actually a blocker. So what this is going to do is this is going to keep a block right here. So it's going to block until those two are done, and we've gotten the signal that both of these are done. But that's a very high level view of what a Go routine is. So first, I want to talk about what is concurrency and what is parallelism. So we talked about before, this is what's really happening, where we have this one main thread, and then we're spinning off more threads that are going to be happening at the same time.
Wait groups in Go. In the lower part of the screen, I created a function that simulates a process that takes some time to finish. It will sleep a certain amount of milliseconds and then print the given integer value. The duration of the sleeping period is determined by the working duration constant in the upper part of the screen. As you can see, even though I created a loop that iterates from 0 to 9 and calls the long-running process function in a concurrent Go routine, I don't get an output with the numbers. This is because the Go routines don't have enough time to finish the working duration before the program ends. Therefore, I'm adding a sleep statement to the main function. 20 milliseconds is enough time for each concurrent Go routine to reach the print statement. However, if this was a real example, a sleep statement would not be a feasible solution. In real examples, usually one does not know how much time a long-running process exactly takes. Imagine this was a database or web request that could vary by several hundred milliseconds. Using a wait group is much better than a sleep statement. So I'm creating one right before the Go routines are issued. I think of the wait group as containing a simple counter. It counts how many Go routines are still running and did not finish yet. I'm using the add function of the wait group to add 1 to the counter for each Go routine that will be issued inside the loop. In order to use the wait group inside of the Go routine, I have to pass it to the function. The compiler is not yet happy with my code. It tells me that the wait group cannot be used as a copy, but only makes sense if I use a pointer. Remember, in Go, if you pass a non-pointer value to a function, Go will use a copy of that value inside the function. Wait groups must not be copies if passed to another function. Inside the Go routine, I'm calling the done function of the wait group after the defer keyword. This will decrement the counter by 1 at the end of the function, indicating that one Go routine is finished. All I have to do now is wait for all Go routines to finish after the loop or, in this example, before the program does end. It works. By the way, the order of the numbers is a bit random, since all Go routines will be started almost at the same time. Now, it doesn't matter what working duration I choose. The code will work every time. Please consider liking the video or subscribing if you have learned something. What working duration I choose. The code will work every time.
So, if you ever wanted to 10 and Go routine, next, I think it's like 40 something days all the way through here. So we spin off another instance, which is going to be running here. And then once we go down here, this wg.add1 is going to be happening on this original thread. Then when we hit this go func again, we're going to spin off another one and we're going to be running it here. So then these are going to be running, but the main program is going to be on this one. So then when this one terminates, the whole thing is going to terminate. These are just going to be left dangling and they're just going to disappear into the void. So we need to make sure that we have a blocker here. So this wg.wait is actually a blocker. So what this is going to do is this is going to keep a block right here. So it's going to block until those two are done. And we've gotten the signal that both of these are done. But that's a very high level view of what a Go routine is. So first I want to talk about what is concurrency and what is parallel. But in reality, they're not necessarily going to be happening at the same time. So there's two ways this can happen. The first way is going to be if it's running concurrently. So concurrency basically means that we're going to have multiple threads or processes running in, they're going to be interleaved with each other and they're going to be happening at the same time. You can imagine if I'm sitting here trying to cook something, if I need to cut up vegetables and I need to cut up meat, I'm only going to be able to do one of those two at the time. But if I go ahead and I cut up half the meat, then I cut up half the vegetables, and I go back and cut up half the meat, then cut up the other half of the vegetables, that's concurrency. I'm doing two different processes. They're starting and stopping, overlapping with each other. So a visual example of this would be, we get down in here, and I'm going to set this to be, let's make this teal. So this group right here, I'm going to put a box around this right here. So this group right here is my first group, and then I'm going to make another box over here around this group right here. So these two functions are going to be executed differently based on whether this is concurrency or parallelism. So in a concurrent world, we're going to have one stream of executions. We have access to one thread. So what we can imagine is happening here is we have like maybe our green is going to run for a little bit, and then that's going to get intermixed with our teal here. Or I guess that changed the color. I'm dumb. So you get the idea. So we have our teal here, and then we're going to have some green running next. So then green will run for a little bit. And then maybe after this, we're going to get some more teal running. And then maybe this will run for a while, and then it'll complete. And then finally, we need to run this for a short period more. And then finally, that will complete. We'll go back to main. So these two are getting mixed in together. Different lines are happening at different times. We could have this defer happen, and then 3 iterations of this happen, and then this happens. Completely indeterminate. We have no idea what order they're going to happen, and we can't rely on the order. We can't rely on this happening before that, which is something that you're going to get into in more advanced concurrent topics, but we need to make sure that these are synchronized properly. But then in a parallel environment, this is going to happen very differently. Just realized this is a different color green. Let me fix that. So in a parallel environment, this is actually going to be happening differently. We can imagine that these will, instead of being stacked on top of each other, these are going to be happening next to each other. So this will be running here, and then right next to it, this will be running in parallel. So this will be happening on a different CPU core. So on another CPU core, we're going to have these two running at the exact same time. And the way you actually do this is by setting a variable within Go called Go max procs. That's going to basically define how many different CPU cores we can use. By default, Go will just read however many it has access to and set that for you. So you don't actually have to do anything to set this up. If you have access to multiple cores, Go will go ahead and do it parallel. But if you only have one, it'll use concurrency policy, so it just depends on what you have access to. So you don't really have to worry about this, but this is just a conceptual thing that you want to make sure that you understand, is that it can either be parallel or concurrent. So with all of that out of the way, let's sort of talk about the key concepts that are happening here. So with those sort of concepts out of the way, let me show you this code actually running. So if I go over here, I have this pulled up, and if I just do go run main.go, you're going to notice that these are happening. We're getting first and second mixed into each other. Here on my computer, this is a 12-core machine, I believe. So these are running in parallel, but it's indeterminate which one's going to go at what time because it's just this random sleet. But you can see these two are happening at the same time. They're being mixed together because they're running in a separate thing, but our main process is being blocked by this wait group. So with this sort of basic example out of the way, hopefully you get the idea of what a Go routine is. Let's talk about some of the more key concepts here and the sort of things you're going to need to actually use this in real life. So the first thing I want to talk about is a wait group, and that's something that you're already seeing being used here. But a wait group is basically just a way for us to block the execution on our main thread until we're done using all of our concurrent channels. This would be very useful. Say, for example, this were an API route and we wanted to go ahead and fetch from two different external sources at the exact same time. We would just have a wait group here that would wait for both of them to be fetched. We would do all of our logic on the results down here and then send it down to the user. I actually use this within Insider Viz in a couple different places. This makes it really easy to do simultaneous API calls. So going back to our example over here, what the wait group is actually doing under the hood is it's actually just set, it has a little internal counter is the best way I like to think of it. And that counter is going to be incremented or decremented based on the status of our actual, based on the status of our current Go routines. So if we set this over here, I can just say at the initialization, WG is going to have a counter of 0. So up here, we have a counter of 0. Then after we add 1, our counter goes up to 1. Then we go ahead and we defer waitGroup.done. But here we're putting the defer keyword in here. So it's only going to set WG to done when we complete this method and this method terminates. And this method isn't going to terminate until this for loop completes. So this defer WG.done is going to happen at the end of this Go routine. And what this WG.done is going to do is it's going to decrement our wait group down by 1. So here I'm just going to leave this at 1 for now because this has to execute in parallel. Then we're going to go down over here. I'm going to say WG is now going to be equal to 2 because we're adding another one. We can go ahead and we can say that this is still going to be going. And then finally down here at the end, we can say that our 2 Go routines have completed. It's deferred. It's down to 0. And once it's 0, this WG.wait will stop blocking. This will just block until this is not 0 anymore. And once it's 0, it's going to go ahead and print out done, and then we can continue on. The way it does this is because it has a shared memory reference that it's going to be pointing to, and we can pass that data back and forth between our channels. So with all that said, we can run these two things in parallel. How do we get data in and out of these Go routines? And the answer to that is channels. What is a channel? A channel it does this is because it has a shared memory reference that it's going to be pointing to, and we can pass that parallelism. So we talked about before, this is what's really happening, where we have this one main thread, and then we're spinning off more threads that are going to be happening at the same time, but in reality, they're not necessarily going to be happening at the same time. So there's two ways this can happen. The first way is going to be if it's running concurrently. So concurrency basically means that we're going to have multiple threads or processes running in. I'm going to say WG is now going to be equal to 2 because we're adding another one. We can go ahead and we can say that this is still going to be going. And then finally down here at the end, we can say that our 2 go routines have completed. It's deferred. It's down to 0. And once it's 0, this WG.wait will stop blocking. This will just block until this is not 0 anymore. And once it's 0, it's going to go ahead and print out done. And then we can continue on. The way it does this is because it has a shared memory reference that it's going to be pointing to, and we can pass that data back and forth between our channels. So with all that said, we can run these two things in parallel. How do we get data in and out of these go routines? And the answer to that is channels. What is a channel? A channel is one of the most useful things in Golang's concurrency, and it is what allows us to pass messages back and forth between different go routines. It is effectively, the way I like to think of it, is a sort of pipeline. It's a pipeline that we can use to send data from one place to another between these go routines. So remember our example earlier where I said we have our main thread here. So our main thread is going to be running down here. And on our main thread, we are going to go ahead and we're going to create this channel C. So this channel C is going to be created somewhere in memory. So I'm going to create this over here to represent our memory, and I'm going to call this guy right here. This is going to be C. So this is our channel C. C is going to exist over here, and it's going to be empty at the start of our program's execution, and that's going to be created right about here. And then we're going to spin up this go function here, and we're going to be using C within here. So what's nice about Go is it can just encapsulate variables, so we just pass variables into an anonymous function, even though we're spinning off another thread here. So our Go function here is going to create another thread over here that's going to execute, but if we pass any variables in here, those are also going to get passed in here, so we can use them in there. It makes it really nice. You don't really, it's a lot easier to deal with passing variables back and forth between Go routines and stuff and functions in Go than it is in something like C. This video is not going to get into stuff like scoping and all that stuff that is way beyond the scope of this, but just know that if we just use C within this anonymous function, it'll be used correctly and scoped correctly. So no issues there. But now with that out of the way, we have these two different threads that are running, and we have our C down here. So within this Go func right here, what we're going to do is we're going to go ahead and we're going to run this for loop. So all we're doing is we're just summing over I. So from 0 to 100, we're summing nothing, or I guess 0 to 99. So 0 to 99, we're summing, nothing special here. And then down here, we are going to do sum pointing to C. So what is that doing? That's going to take this sum variable and it's going to put it into C. So that means that from this thread over here, we're going to take our end value here, and that's going to get pointed into C. We can imagine at this point in the program, we're going to be loading into this channel. We're going to be loading the number, whatever that sum is. It's like some number. We'll just say we're loading sum into here. So our sum variable is getting loaded into C. And then in this main thread over here, we're going to read out the result of that. We're going to read that out into here. So we're going to put that in there. This is beautiful drawing, by the way. So we're reading that out there. So we're going to take it and we're going to put it in here and we're going to pull it out there, and then we can print out that output. And this is a blocking method. So this right here is going to block execution until it's complete. So until we get something out of this channel, it's going to block. So that's what makes the synchronization on this super easy, is we can just run this for loop over and over and over again. And this will not just terminate out of nowhere without this. So if I go over here and I just do go run main.go, it's going to say IDX from each one, and it'll say output is this. And that is just sum getting pointed into here. What's interesting is if I remove this right here, if I remove all this stuff, it's not going to print out all of this. If I do go run main.go, it's not going to print anything out because we're not blocking. We're not waiting for this other one. So this is just going to die and float out in the void. So we need to make sure that we're pulling out of this channel, and then we're doing that. That's a very basic example of what you can do with channels, but effectively just think of them as ways to pass messages between different threads and different Go routines. It makes it super easy to synchronize them and keep data going back and forth. There are more advanced concepts on these. If you want to see a deep dive on channels, let me know, but this is the sort of introduction. Is just think of them as this little block in memory over here that we can put data in and pull data out at will. And the last thing I want to talk about today is going to be mutex. So a mutex, or a mutual exclusion, is a way for us to ensure that one place that one that if we have a spot in memory, that spot in memory is only going to be written to by one thing. And why is this important? So remember earlier, we have multiple things running here. So in this case, I'm actually going to be spawning off 100 Go routines right off the rip. So this is going to be, there's going to be 100, just use the 2 for now. But imagine we have these 2 threads running in parallel, and then we have this over here. And this, what we're going to be updating is going to be this map of key. So that map of key is going to exist somewhere in memory. So we can think of our memory as this over here. This is a terrible little recreation of memory, but you get the idea. It looks something like this. And imagine right in here, we have our memory. We have whatever this s.nummap key is going to be. Imagine it's right here. And imagine we have all of these different threads. We have 100 of these, and they're all trying to write to this one little spot all at the same time. It's going to crash. So what we need to do is we need to create a mutex, which is a mutual exclusion, which will make it so that only one of them can write to it or read from it at once. So the way we do that is we can go ahead and just create this safe counter thing. So all this is going to do is this is just going to create a mutex and a map. So then within this map, I can go ahead and say, okay, within this method, so I'm adding a struct method to this. There will be another video on those in the future, but in this struct method, what I'm doing is I'm just going to go ahead and I'm going to lock the mutex. So a mutex has 2 methods, it has a lock and an unlock. A lock will make it so that anytime you try and access this, you can't do it. And an unlock will make it so that anything else can now access it. So one of these guys will go in, one of these threads will get there first, and when it gets there first, it's going to lock it. So when it locks it, all of the other ones are going to be blocked on this lock. They're not going to be able to do anything until it unlocks. So it'll sit there and wait on the other ones, and then that one will be able to go through, and they'll be able to write to it. So it'll just set it to equal to whatever value pass in here. It's a very dumb example. You wouldn't do something like this in real life, but this is just to illustrate the sort of point here of writing only one thing to memory at a time. So we go ahead, we do that, and then we go ahead and we defer s.mu.unlock, and like I said, unlock will free it and allow the others to actually mess with it and edit it. So what we can do here is we set up our save counter, we initialize a new map in here. I'm going to create a wait group to wait for all of these to go through and do their thing. Then I'm just going to call this go routine down here, which is going to try to add to all of them at the exact same time. And then at the end of this, whatever value is left in here is just the one that got to it last. So if we go ahead and run this in here, we go ahead and do that. We're going to get 99 was the last one. If we run this again, we'll probably get a different number. Oh, we're getting lucky here with 99. Oh, 83. There we go. So we just keep running this over and over again. We're probably going to get different numbers every time. So the whole point of this is that it's indeterminate. We don't know which order they're going to run in. But if we went up here and we got rid of our lock and we didn't lock to it, and we do go run main.go, it's going to explode. And the reason it explodes is if we scroll all the way up here, it tried to do it like a million times, so it crashed. But if we go here, it's going to say concurrent map writes. So we're trying to write to a map at the same time. We're taking 2 different methods, are trying to write to it at the exact same time, and then it breaks because that reference is going to get broken. So we have to make sure that we only have one writing to it at a time. The way we do that is we accidentally close our editor, but I did save it. So if I just do go run main.go, it's fixed. So with all of that said, hopefully that gives you a better understanding of concurrency, gives you a good introduction on this. This is just a very preliminary sort of crash course on how all this stuff works. But I think that with these sort of skills, you can go ahead and actually do some really useful stuff. If there's one of these topics you want to see broken down more, let me know. data